All right. Hi, everyone. Welcome to ITC Battlestar Galactica, a talk and discussion series about galaxies. So I'm Erin Nelson. I know most of you, I think. I'm a Hubble Fellow in the ITC, and this is Sandra Takela. He is a CFA fellow. I'm trying to convince him to move downstairs to be in the ITC hall with me, but no luck so far. So the reason we wanted to do this was, the situation right now in our field is kind of, we have these cosmological hydrodynamical simulations that can essentially, reproduce the universe at pretty fine-grained scales. And we have the computational ability to really understand galaxy formation from the beginning of time to now. And especially with the launch of the James Webb Space Telescope in a couple of years, we're really at a point when we thought it would be useful to see what the state of the field is and to check in about what we know, what we don't know, and what the most productive avenues for progress are. And so, you know how these things go. Whenever you go to a conference, everyone is just always talking about what they agree on. The observers are always like, oh yeah, I kind of see your model in my observations. Sure. Everyone's like trying to be polite. The observers don't really want to tell the theorists that they're wrong, and the theorists don't want to be wrong. I get it. Like, I'm a Minnesotan. I understand where this comes from. I'm not particularly confrontational either. But you only really make progress if you kind of highlight the things that you don't agree on, especially in observations and simulations. So that was the idea behind this format. So we're gonna we'll have two speakers, 20 minutes or 40 minutes, whatever ends up happening here, and then another 20-minute talk. And so please ask clarification questions during the talks. That would be great, as long as you guys are okay getting interrupted. Is that okay?
Sure. If you can stay all here 2 hours, that's fine.
Okay. Okay. But instead of having a standard Q&A after the first talk, we'll just save up your questions, and we'll do a discussion and questions for both speakers after everything's done. And Sandro.
Yeah. So I think really the goal is to have a discussion. Like we said, it's like 20 minutes at the end, but really a discussion. So it might even, it's possible to get longer. So if some people want to leave after the talks or so, they can do so. But of course, we want to really highlight that we have a discussion, that we try to see that you understand everything in the talks, but also what are the next steps maybe in the field to go forward. And so now, as you know, we have two speakers here today. So we start with Daniela Calzetti. She is going to give the CFA colloquium tomorrow, and we'll get a very nice introduction. I'll try to be very brief today. But still, Daniela is a professor at UMass, so she came over this morning by car. And she's also the head of the Department for Astronomy. She has, of course, done really great work on all kind of things that you see here in this picture, basically, really starting from star formation on small and large scales, but also on the IMF, and of course also on the dust attenuation and dust properties in these galaxies. And so she's really a key player in this field. We can just look up ADS, and you see the first most cited to the four most cited papers have all 500 citations or more, and the one on the top has 3,000. So it's she's really a key player here, and so I'm very happy that she said yes, she's coming here extra day earlier before the colloquium to give us a short presentation on spatially solved star formation.
Thank you. I hope that the presentation was recorded, because I need some of those nice false things that you said about me. Anyway, so I don't want to make it too long. The joke that I like to say is that if Rob Kennicott got 1 cent for every time this picture has been shown, he would be a billionaire. So I'll send out the collection basket later. But the point of this picture is that it correlates very nicely for whole galaxies, okay? So each data point is an entire galaxy. The surface density or star formation rate as a function of the surface density of gas, and the two are correlated. Now, the puzzle that has been, and the question that has been asked for over 20 years, actually, since this has been shown in some form or another since 1977, you can do the math. The question is, what drives this, right? Why do we have what is obviously a nonlinear relation when you include the entire gas of the galaxy and in the horizontal axis? What is driving these over superlinear slope? And in particular, is that because your efficiency is increasing, so you are more efficient at converting gas to stars, or the dynamical timescales change. Just as a reminder, the relation between these two can be expressed, so the ratio between the subformation rate and the mass of the gas is the ratio of the efficiency of subformation, the proper efficiency, how much of the mass of the gas is converted in star at each specific time scale divided the time scale. And the time scale is coming from the subformation rate. Oftentimes, this ratio is called 1 over the deposition time. So the correlation is tight and has been actually verified at multiple redshifts, at least up to about redshift 2 or 3. These are two plots from two recent papers, one by Rainer Genzel and the other by Linda Tacconi, showing virtually similar versions of the same plot. I'll concentrate on this one, which is a little easier to read. Practically what it's telling you is that as your galaxy becomes more strongly star forming, so this is the ratio of the specific star formation rate of the galaxy divided the mean star formation rate of all galaxies of that epoch. So when your galaxy is actively star forming, its depletion time scale is shorter, meaning it's converting gas into stars at a more rapid pace, which is the same concept embodied by this second picture. It's just that it's more recent, so they could actually do a much more specific analysis of different sub-dependencies. But the main point of this figure is this is a verified trend that is really true at all redshifts. Now, I don't want to go into the detail that if you convert this deposition time scale, this trend, into the standard Schmidt-Kennigat relation, the slope is 2. I don't want to get there. Okay? Okay, so how can we discriminate between the increase in efficiency and the change in the time scale? One option is to look at individual objects. So, for instance, there is a nice superstar cluster in this nearby galaxy, and when you calculate the efficiency directly, so the efficiency can be measured directly, and unfortunately not in many situations, when you can measure the mass in star, measure the mass of the gas, take the ratio, okay, instantaneously. That's an efficiency. That's the direct efficiency. Well, when you look at globular clusters, superstar clusters, other also general clusters in general, where this type of game can be a little easier than in general populations in galaxies, you tend to recover efficiencies that are pretty high. Bruce Elmegren claims as high as 80%. I have not measured anything above about 30 to 50%, but it's pretty high, much higher than the 1% time scale you need if you actually just convert straight this relation to a time scale. So clearly, there is obvious evidence for increased efficiency as you go to the subgalactic scale of galaxies, especially if you are looking at single individual populations of relatively small scales. I actually mentioned the scale over there is 20 parsecs. Each galaxy here is tens of kiloparsecs, so the scale is completely different. There are also regions when the efficiency is decreased, but that's often attributed to effects like turbulence, magnetic fields, so there is an external effect. It's nothing to do with the intrinsic physics or how the gas converts into stars, at least in these cases. However, that doesn't mean that everyone agrees. So if you take this a picture from a paper by Mark Krumholz from 2012, again, what the vertical axis, given in a different symbol, is still the surface density of star formation rate. The horizontal axis is the surface density of gas, but it's divided by the free-fall time scale. So the time scale it chooses, Mark chooses, is the free-fall scale, time scale of that specific system. Now, the paper goes through, most of the paper is devoted to defining what the dynamical time, this free-fall time scale is for each system, because you're moving from regions in galaxies all the way to whole galaxies, and the free-fall scales can be very, very wildly different, and it takes a lot of careful attention. And what it recovers is a fully linear relation. However, there are also critics to the way these free-fall time scales have been determined. On this other plot is a slightly older paper by Emanuele Daddin, in which they combine the local measurements with high redshift measurements, And what they chose was the standard rotational timescale, right? The angular velocity timescale of the galaxies, which is the standard measurement that is used to show is what is called the Silk-Hamilton law. And however, if you define the horizontal axis as the ratio of the gas to the dynamical timescale, you generally cover a nice linear relation, which would be, of course, would be telling you that the timescales are important. But maybe efficiency also is important, as we saw before. So the two clearly are not a single parameter in any of these relations, and maybe you are asking the wrong question. One other point that I would like to make in the 40 minutes left is that, is that when you move from galaxies to regions, say molecular clouds, and actually we have a major representative here in Charlie of how you can actually try to look more correctly at this type of problems, is that when you move from galaxies to regions within galaxies all the way to clouds, you lose this nice tight correlation. It becomes broader. There are many explanations why that happens, and sometimes it actually loses completely the standard relation that we see. It becomes almost a vertical line. Now, many among us have tried to see relations here in these type of plots, but if you remove all the lines, it's a scatter plot. But one thing is clear, okay? As we go from the whole galaxies to the regions within galaxies, we are concentrated to regions that are increasingly more dense, okay, denser, which means that the first thing that we have to understand is how we transition from H1 to molecular gas, from atomic gas to molecular gas to the dense gas that forms the stars, okay? And do we have any relation between, so is this driven simply by physics, or there is also the external trigger of galaxy feedback? And how does that work? The other problem we are having that is often underappreciated is that the two axes are non-congruent. This is a dissipative tracer. You're just measuring something that is now, happening now. This one is a non-dissipative, meaning that you're oftentimes prey to a much longer time scale than the one in which you're measuring the gas. And that's a problem, because when you move from whole galaxies to regions within galaxies, you're actually making wild assumptions on both axes, more on the vertical axis than the horizontal axis. So, if anyone can find in the universe a galaxy that has molecular gas, but not atomic gas, let me know, because I would like to know where that galaxy is. So when authors make the point that in order to understand the Schmidt mechanical law, we have to measure the star formation rate and use only the molecular gas on the horizontal axis, they're telling me that there are galaxies that don't have atomic gas. And that's not a possibility. The H1 is distributed far more broadly. But the moment you lose the H2 because you have converted it into stars, you're automatically also converting some of the H1 back in H2. Yes?
How about a galaxy that has molecular gas but is no star forming?
That's even more interesting. Are there any?
See 524.
524. I don't.
It's a giant galaxy center of a group, and there is ALMA data showing molecular gas in the center, rotating disk around the 10 to the 8 solar mass black hole. Zero star formation, deep UV images in HST, 0 plus.
It could be that it's a highly turbulent central region. As they measure the
disk that is sort of turbulent. So it's not a star-forming disk. You see it in ionized gas a little bit.
Okay, so I mean the central molecular zone has puzzled our colleagues for a long period for a long time, because it has a lot of molecular gas, but very little star formation. At least if you relate it to the Schmidt mechanical law, it's below the Schmidt mechanical law. I think I have a picture somewhere. And the reason there is that you have a strong turbulence, magnetic fields, and a host of effects that are external to the physics of star formation itself, but they influence the efficiency of star formation. So I'm not familiar with that specific galaxy, but if there is a lot of turbulence for it, that might prevent the gas from collapsing. So, but the point that I wanted to make on this point is that we can move from H1 to H2 to denser gas and increasingly denser components of gas. At some point, the Schmidt-Chemical law will be stars versus stars, if we are not careful how we try to interpret this relation. So the whole gas components have to be included when you're trying to understand what is happening to the theory of stuff, when you're trying to build a theory of star formation. You cannot do one without the other. The other point I want to make is that stars, so you measure star formations by measuring the emission from stars. Stars are non-dissipative. You take the UV emission, well, regions that are no longer forming stars, or have not formed stars for a long period of time, still emit UV. Okay? So depending on what scale you are relating to, you might actually be measuring something that is not star forming, even if it has UV light. That's the point I want to make, for instance, in the interim regions of spiral galaxies, where oftentimes we have colleagues who measure UV emission and convert it to a star formation rate, forgetting that if you have a 40 million years population that is not active now, even if you have UV, and you do have UV, it's not forming stars. The star formation rate is 0, okay? Even if you have a measurable UV emission. That can represent a problem because it's related to the fact that stars live long lives and are non-dissipative and a non-dissipative way of measuring your vertical axis. Okay, so the diffuse light from the older populations needed to be removed, and that's something that is not often appreciated. Now, let's move into the detail for the last 4 minutes. 5, 4, 3. Okay. Why have I made that long introduction? Because the point is that, okay, let's move away from whole galaxies. If you're trying to understand an entire galaxy and many different galaxies, it's going to be a problem. So let's zoom in into a single galaxy. This has been done, okay, it's nothing new. What we are bringing new to the table is the ability to actually measure the long wavelength emission, and so measure the dust mass, and therefore the gas mass, if you have an appropriate assumption for the dust-to-gas ratio, of a galaxy that is forming stars now. So we'll have relatively limited problems of diffuse UV emission, because there is a lot of current star formation in the region. So this is an example of how we did the derivation of the gas mass. So you take the infrared emission, you fit the IRSCD, you derive a dust mass. These are the Daniela models, and then the dust-to-gas, with the dust-to-gas ratio, you convert it to a total surface density of gas. This is how it looks in different regions. So if you have a region that is active at 24 micron, so it's very bright at 24 micron, will give you a strong signal, which is evidence of a strong 24 micron, which is typically evidence of active star formation. A very quiescent region, so this is a sort of blank spot, will give you very little 24 micron. That's the second point from the left. And you can actually immediately discriminate between the strongly star-forming and non-strongly star-forming regions, and pixel by pixel reconstruct the Schmidt-Chemical relation. So if you do it for just the molecular component, okay, now the scatter is large, but that's what you expect. I have 2 vertical lines that show what you can expect from stochastic sampling of the stellar initial mass function. Plus, you have the stochastic sampling of the clouds. Okay, you don't have a huge sampling of the clouds, and indeed the scatter decreases when you go from regions that are 400 parsecs in size to regions that are 1.5 kiloparsec in size. So the slope becomes flatter and the scatter decreases. Now, if you plot these relations as a function of the scale of the region that you're sampling, you see clearly that there is a trend from a slope of 1.5 down to the slope that is almost 1. Okay? What does it mean? And actually you see it in more than just this one galaxy. We have done the experiment on another couple of galaxies. What do you see? And this is actually how the scatter behaves. You have a large scatter in the relation at the smallest scales, and the scatter decreases. What does it mean? It means that you're counting clouds. So the molecular mechanical law is not giving you anything physical. You're just simply counting the clouds. Unless you can put the clouds on top of each other, which we know it doesn't happen. Also, because we have a filling factor that has been measured by Adam Leroy, I think in 2009, which is around 15%. So of these 400 parsec squares, only 10% is actually filled with molecular gas. Because of that, you can't really use the molecular law. But if you use the total gas, you generally find a smaller scatter and a much tighter relation. And this relation, the slope of the relation, doesn't change with the scale you're looking at. This is telling you that there is something far more specific and fundamental about taking into account the entire gas components, H1 plus H2, as measured by the dust surface density, than just looking at individual components of H1, H2, or denser gas components. So I think that what you can conclude from here is that you want to look at the total gas. If you want to understand the large-scale star formation, how star formation works on large scale. I have one last slide on the comparison with this recent paper by Orr, Hopkins, and collaborator, and in particular how they see in their simulation, how do their simulations behave. They have these 5 simulations, which is they simulate individual galaxies and try to understand how star formation works in their case. And so this top panel is one of their figures. It shows the star formation law, same surface density of star formation rate as a function of gas. What they call neutral hydrogen is actually the full gas component, H1 plus H2, and what they call cold and dense gas approximately is molecular hydrogen. Okay, they don't have the exact same definition. But practically they go from a slope of 1.5 to roughly a slope of 1. Then they look at the spatial behavior, but they only look at it for the molecular gas, the equivalent of the molecular gas, what they call the cold and dense. And what they find is that the scale doesn't change with the slope doesn't change with scale. In their case, it remains roughly around 1. Okay? So the question is the simulation too simplistic, or are our observational results incorrect? Right? Because we find a trend, a clear trend, that if you go from 0.1 kiloparsec to 1 kiloparsec, you should go from a steep slope to a shallow slope, roughly about 1. They don't find that. Well, the problem is our clouds are clouds. Whenever you have a mass, you have a size. And we simulated them as incompressible clouds, okay? So our model allows it's just a toy model that allows us to put real clouds inside the bins. In their case, it's unclear whether they can actually simulate the fact that if a cloud has a certain mass, you can't really put another cloud inside it. So if you don't have incompressible clouds, you will recover the global 1-to-1 slope, because you're counting clouds also in this case. It's just that here you don't have them incompressible, so you're less subject to the fact that your slope of 1.5 is actually coming from the fact that you're stochastically sampling the clouds. And you're actually counting them only when you are above a size scale of about 1 kiloparsec. So the slope of 1.5 is not intrinsic. It's actually due to the fact that you are randomly sampling the cloud function. Okay, conclusions. So we are beginning to connect the local to the global. Okay, but it's important, in my personal opinion, to take into account all gas phases. You can't really select the gas phase you are connecting to star formation. You have to really keep everything in the same bin. You also need to make sure that you clean your star formation rate indicator or any contamination from diffuse light. Okay, in a starburst galaxy, it's probably not a big concern, as in this case, but it's going to become a concern when you look at less active galaxies. The total gas law, where a total gas I mean H1 plus everything else, appear independent of the spatial scale considered. But in the case of H2, we're actually simply counting clouds. You're not really getting anything that is beyond the geometry. You're just mostly doing geometry. That's my point.
Thank you very much. Okay,
Oh, sorry.
Yes. Yes.
Maybe I went too
Yes,
fast.
maybe time for one question, and afterwards we have more questions at the end. Yes?
Well, you can take this to the end if you like. I just had a question about the relevant time scale.
Yes.
So you said you wanted to subtract the diffuse light that would confuse anything but the relevant scale.
Mm-hmm.
And I would just like to understand better what that relevant scale is. For example, are you trying to look at only the most massive stars that are formed with a short time?
Right. So, it's hard to give a time scale, but I would say the time scale of a massive star should be the one you're most concerned with. So it should be no more than about 10 million years. The most recent stars. Now, one common mistake that I've seen in the literature is that people say, oh, I'm taking the H alpha and measuring the star formation rate of a time scale of less than 10 million years, because that's when, that's not entirely true, because the way the star formation rate indicators are calibrated, they're calibrated over a scale of 100 million years. So if you're taking your H alpha emission and you're using the same constant as everybody else, it's a 100 million year scale. And one has to be careful about that. So you will see that if you measure the far UV, corrected for dust attenuation, the H alpha corrected for dust attenuation, they give you the same number. It's not because, it's not necessarily because star formation has been constant over that time scale. It's because the calibrations are made to make the two identical. And we have to be careful about this because it's an important, subtle but important point.
Okay.
Okay.
Discuss more afterwards.
All yours.
Good. Okay, so the second speaker is John Forbes. He's well known here. He's an ITC fellow. John did his PhD at UC Santa Cruz and came here 2.5 years ago. And yeah, he works on a wide range of topics actually. So he works of course also on star formation. That's why he's speaking in this session. But also he has done works actually on like general scaling relations of galaxies across cosmic time, and also even on brown dwarfs in the local universe actually. So yeah, John, take it away.
Oh, thank you all. So I have some bad news for the organizers. I don't think I really disagreed with anything Daniela said, but we'll see. Okay, so in the spirit of Battlestar Galactica, I'm going to discuss 3 star formation models. And I wanted to, but first I wanted to sort of separate the topic of star formation on galactic scales into 2 issues: the star formation law, which we just heard about in detail, and star formation history, which is what you actually see as a function of time in a galaxy. So the star formation law is what you need to understand this relation, the relationship between surface density of gas and star formation. And simulators are probably overly, well, maybe not overly, but very concerned with this this question because we have hydrocodes that evolve galaxies in time. They tell us where the gas is. So what we need to do is put in a rule for how you form stars. But there's another question, which is what sets the actual star formation rates in a galaxy, and maybe it's independent of. Maybe there are principles besides what the gas surface density is, which sort of set the star formation rates of galaxies. And that's sort of interesting in understanding a relationship like this between the total stellar mass of galaxies and their star formation rates, so the star forming main sequence. So let me just show you, let's focus in on this first question first. So I'm going to, maybe no surprise to people here, to talk about this model, which is variously called the bathtub model or the equilibrium model or the gas regulator model. And the saga here starts more than a decade ago now, where these folks who simulate galaxies, simulate cosmological volumes and hence galaxies within them, realized that in their simulations, their galaxies tended to be in equilibrium, meaning that they were consuming stars through star formation and outflows at basically the same rate that they were gaining mass. They were consuming gas at the same rate they were gaining mass. And this is remarkably close to 1 here, so it's within a few percent. Yes?
Is it remarkable?
Well,
I mean, like,
Well, okay, I'm going to make an argument about why it's not remarkable, so I'm not going to disagree with you. But I think I don't know that anyone expected this a priori. So, well, yeah, and especially with the paradigm of mergers and so forth, I think this picture was new and surprising at the time. I mean, I remember the coffee discussion where the Dave et al. Paper I referenced on this slide came out, and they said, we have this model where the gas mass of a galaxy stays constant over cosmological timescales, and everyone's like, what? We were surprised, I would say. Okay, but this is why it's not surprising. So if you write down just the rate of change of the gas mass of a galaxy, you just take into account all the places it can go. You can add gas through external accretion. You can lock stuff in long-lived stars. That's what this FR is accounting for. And you can remove stuff in outflows. If you then just say that the star formation rate is just the gas mass over some time scale, and that the outflow rate is proportional to the star formation rate with constant eta, you can write things down this way. And then finally, you can just absorb all these numbers into one time scale, the loss time scale, or the gas processing time scale, whatever. Then you get a very simple equation here. And actually, I should point out, no huge assumptions were made going from here to here. These are all definitional. But the assumption that you make is that this time scale varies slowly. If that's the case, you can write down the solution to this equation analytically. And it's just, you start off at the initial value, and you adjust to the equilibrium value, and you do so on this time scale, on the time scale T loss. So as long as the loss time scale is short relative to other time scales you care about, you should expect the galaxy to be in this equilibrium state where its gas mass is equal to the accretion rate times the loss time scale. And in fact, the star formation rate is equal to the accretion rate divided by, this number is about 0.5 plus the mass loading factor. And I think this is profound because you're basically saying that the star formation rate in the galaxy doesn't care about the star formation law, which is all enclosed in this T loss term. And instead, it's just being set by external factors. Now, there is a bit of a question here because we don't actually know what the value of this mass loading factor eta is. So I think I show this plot in all of my talks, but this is the mass loading factor that people use as a function of mass for a bunch of different simulations. And you can see that there's sort of order of magnitude or more disagreement among all these lines. And what that means is that we can't distinguish between a scenario where basically all galaxies across all time are in equilibrium or only massive galaxies are. So that's what I'm showing here on the left. The top panel is if you assume that the mass loading factor scales very strongly with mass, so that it becomes 100 in dwarf galaxies. And I'm showing halo mass versus redshift, and galaxies grow according to these yellow lines here. And basically, in this strong feedback case, you get that basically all galaxies that form stars are in this state. If you have weaker feedback, where the mass loading factor is only half for all galaxies at all times, you find that dwarf galaxies fall out of equilibrium because they're very gas-rich, but they're not forming that many stars. So their depletion times are quite long, and if eta doesn't increase itself to keep up, this loss time also becomes very long. Okay, so that's the story with equilibrium models. Now let's turn to the question of the star formation law. So The star formation law is very difficult to understand from first principles, so I'm going to rely a bit on the observations as well. So the first point to make, which everyone presumably already knows, but is that if you look at the molecular gas and the atomic gas in nearby galaxies, you find that the molecular gas is what's most closely determines the star formation rate. And if you divide it up into patches and look at these relations, Daniela showed these. If you look at the total gas versus the star formation rate, you find that there's this turnover here. But if you only look at the molecular gas, you get a very nice straight line, linear in this relation, which says that the depletion time is a constant of 2 gig years in massive galaxies in the molecular gas. Something that I think is important to point out is that so the blue and the red is basically the same data from the previous plot. If you also, and the point about that is that these galaxies are going to be roughly solar metallicity. But if you look at the data for the Small Magellanic Cloud, which is shown here in green, and for high redshift systems, which are also low metallicity, you find that there's a similar behavior, but the turnover occurs at a higher surface density. And so this is an important metallicity effect that you have to take into account in a successful model. So now the question is, how do we, given these observations, how do we go about trying to understand them theoretically? And there are two broad approaches, top-down versus bottom-up. Top-down says that it's galaxy-scale processes that set the star formation law. And bottom-up says it's cloud-scale processes, and you add up the clouds. And it's interesting, Daniela's talks seem to imply that that depending on how you looked at it, both of these are at play. And indeed, there are advantages and disadvantages to both of these sorts of models. So in a top-down model, you say, you suppose that the star formation rate is set by the requirement that the rate at which you're injecting momentum into the galaxy must balance something else. So a common choice is the rate at which turbulence dissipates in the galaxy. So if you write that down, you get a very common case of this law. And a generic feature of this sort of star formation law is that you end up with a scaling like this. Now, there are advantages of this sort of model. It's nice that it's insensitive to the small-scale star formation recipe. People sort of rely on that a lot in the simulation community. And it seems to agree with the results of some high-resolution simulations, which I'll show you in a second. And you get a steep scaling of the Kennecott-Schmidt law with the total gas surface density. The problem with this approach is that there's no obvious way to include a metallicity dependence, which seems to be in contradiction to the data, which requires that the sort of transition occur at a higher surface density. And there's also no reason a priori in this sort of model to expect the strong relation that you in fact see with molecular gas. The bottom-up approach says that the star formation rate is, you just write down basically, you say that the star formation rate is the gas surface density divided by the freefall time, the sort of natural time scale, and it's regulated by this molecular fraction, which you have to go to a lot of trouble to try to estimate from first principles. So it's nice because as a result of including this H2 physics, you get a metallicity-dependent turnover in the Kennecott-Schmidt law. There are still problems, of course. It's hard to estimate this constant proportionality from first principles. And as Daniela pointed out, there's some ambiguity over what time scale you should really be using. Yes? Not in any obvious way that I can think of.
According to the galaxy formation models, depending on them, if you're called or not called, one of them are selected.
Yeah, we can talk about that later. I'm not sure. Okay, so I wanted to show this result, this point here, that a star formation law like this is insensitive to the small-scale star formation recipe. And this is this famous result from Hopkins et al. In 2014. So what they did here is they took two different isolated galaxy models, so one that's supposed to have a gas fraction sort of similar to the Milky Way and one more appropriate for a high redshift galaxy. And they basically turned on and off every different switch for what people put into the star formation law in these galaxies. So like if you have a cell, how do you decide whether it's star forming? There are all these conditions people use. And it turns out that no matter what you do, you basically get the same star formation rate. It's especially true here. So what this says is that the star formation law on the smallest scales is not determining the star formation rate, but rather it's the feedback, the strength of the feedback, and you can immediately see that here. If you don't put in any feedback, you obviously get a very different value of the star formation rate. Something that's less widely recognized about this result is that when you change these star formation laws, you in fact get very different states of the ISM. So this is number density on the x-axis, and this is the PDF of the number density of the gas. And depending on which of these conditions you choose, you end up with the gas in a very different conformation. Okay, so that being said, there are sort of many different examples of these star formation laws, and I've just to give you a flavor of what they look like. This is the simplest one. Like I said, you just take the star formation law and you set it equal to the turbulent dissipation rate, and you end up with this nice simple relationship. Here and here you have to do iterative equations to sort of get the FUV right. But when you do that, you can, I just want to briefly mention this, you can make predictions for what the star formation rate should look like in a situation where they disagree. And so that's the movie I showed on the title slide. This is a set of simulations of dwarf galaxies. And basically what we can do is we can divide this galaxy up into patches and use the analytic models I showed on the previous slide to estimate what the star formation rate should be and compare it to what it actually is. And basically, I mean, the striking thing about this plot is that all the models disagree with each other and the simulation. And in fact, the data for the SMC sort of, I mean, I'm not showing it here, but it encompasses this range as well. So the other interesting thing is because this is a simulation, and you can take all these constants that you have to set in these models, and you can measure what they actually are in the simulation. And it turns out that they don't move the points very much. So something qualitatively different is going on in these models as opposed to the simulation, and it'll be interesting to understand like really where that's coming from. Okay, but to conclude here, so the point of the first part of the talk here is that the star formation history of a galaxy is probably nearly independent of the star formation law, as long as the outflows are strong. The star formation law does, however, affect what the galaxy looks like, how much gas mass it has, and what distribution of densities it has. And the star formation law itself may be determined by sort of a self-regulated process, but it may also be determined by what's going on the scale of individual clouds and counting those out. All right.
Is there just one immediate question before we set up for a more discussion session? Okay, so maybe we set up the two of them here. You know, try maybe to sit as well. Everybody else. So maybe that they go sit here.
And no throwing objects, okay? Like the speakers.
So we have now a couple of minutes for discussion. So we try to just moderate it and not make it too, too formal. If you don't have any questions or things you would like to raise,
I have no preference.
You want to stand? You prefer to stand?
No, I was making him choose the one so I can put mine behind his.
Okay, so Charlie?
So I guess I don't quite understand why the top down versus bottom up is always phrased as a versus rather than, it seems to me like it's both. Like the top down sets like distribution of densities of the gas and is regulated on some global scale, but then the actual star formation is happening in a molecular cloud. It depends on the molecular cloud physics itself. So it's like, why is it not just, I mean, we don't talk about it, there's two things happening that are both relevant.
Right.
They're both setting different aspects of the problem.
So I'm mostly going to agree with you, and I think some of the results you showed would also agree with that sort of assessment. I will just say that the particular models do disagree with each other, but that may just be a shortcoming of the models. A particular top-down model and a particular bottom-up model can make vastly different orders of magnitude, different predictions for the actual star formation rate. And it may be just that they need to, I think probably the most successful ones take into account both the cloud scale physics and some necessity of regulating the star formation based on how much FUV you actually need to support the ISM.
Right, I mean, any of those top-down models, those sort of analytic models, they make a whole bunch of assumptions about how the energy couples and et cetera, et cetera. So those could be different just because of the particular details of those assumptions, right?
I mean, if I can add to that, first of all, I agree with you 100% that the clouds matter, the physics in the clouds matter, and Charlie probably can speak to that. The top-down probably has relevance over the larger scales that are, say, of order kiloparsecs or larger, as you said. Maybe so the problem is we don't know exactly where one ends up being more relevant versus the other. So we don't have that scale yet, where we can actually say, okay, we transition from where the bottom-up matters to where the top-down matters. But clearly, as my results have shown, if they are confirmed by other galaxies in which if you take into account the entire galaxy content, gas content of the galaxy, and not just one component, you end up always with the same relation, with the same slope, tells you more or less that this is the top-down matters up to about a few hundred parsecs. Then below that, probably there is a transition zone where below which then you have to worry about the physics of clouds and how the star formation behave. And there you enter in the regime that is often analyzed when you have direct measurements of efficiency, in which you can measure directly the mass in stars and mass in gas. And that's usually of the order of a few tens of parsecs. So down to a few hundred parsecs, top down maybe works. Certainly up to about a few tens of parsecs, the bottom-up works. Where the two transition is probably unclear still. Yeah, all yours.
So I wanted to come back to this sort of messy topic of the total versus molecular gas, right? Because you showed on, like, at first sight perhaps contradictory plots, right? You showed that the slope is actually more constant as a function of scale when you look at all gas. But then you showed that at fixed scale, but a function of surface density, the slope is more constant when you look at molecular gas. And so these are not obviously contradictory, but sort of, I'm still not taking away which one's actually more closely connected with star formation.
I think he and I can have we'll have opposite opinions, so you can start and then I'll chime in.
Yes! Well, thank you. I'm less convinced of that.
Okay, go ahead.
Yeah, I mean, I think the fact that the molecular gas is so strongly correlated with the star formation rate is just a very compelling fact. And this transition that you see when you look at the total gas is really telling you something about transition from molecular to atomic. But I agree with you. I don't know that that's contradictory to the results she showed about.
So I can answer,
Oh,
I can
yeah,
answer
go
to
ahead.
that.
I think I agree that it's clear empirically that molecular gas and star formation rate trace, linearly they trace very well. I disagree a little bit with what Daniela said about the H1, because, take a typical disk galaxy, you're not worried about too much about the metallicity variation. Then whenever you find H1, you never find it exceeding column densities of roughly 10 to 12 solar masses per square parsec, because when you get above that, you go through the phase change to molecular hydrogen. So when you add gas that's basically inert to star formation, at any line of sight, you're always adding a constant, H1, and whereas the H2 is increasing. So it's just an artifact that the slope comes out 1.5 and is constant. It's just, the H1 has nothing to do really with the star formation rate, except to the extent that you go through this conversion, which depends on things like maybe the stability of the disk, say, in the galaxy. At what point does the H1 then collapse and get to higher and higher quantities? That would be my view. But I also think that the two relations that Charlie was mentioning, I don't think there is a big discrepancy between bottom up and top down. I think the top down gets you to the point where the bottom up becomes important and regulates things.
Okay, I'm glad I can disagree with Charlie. Because when you find a linear relation, and that's why I showed the plot that was showing for individual clouds the relation between star formation rate and surface density of H1, there is not a linear relation, right? It's what you call what people call the transition range at 137 solar masses. Yeah, whatever. Solar masses per parsec square, and then it becomes linear. It never becomes linear, reality. So the plot that has been shown, that is shown typically, those are regions that are typically a kiloparsec. Some take, say, 800 parsecs, some take 1.5 kiloparsecs, but they're usually at the kiloparsec scale. So those linear relations are not recovered when you go much below 1 kiloparsec. So all those beautiful linear relations is because you have collected enough clouds in the region to actually fully sample the cloud mass function. At that point, it becomes a linear relation.
Because you're measuring surface density. If you look at just the mass of gas and compare H1 and star formation rates, completely linear, so independent of that. So when you measure surface density, yes, and you average over some volume, you're going to get stochastic. In fact, if we take molecular clouds locally, where we measure very precise star formation rates and masses, there is no Schmidt relation. It's a vertical line.
Right, it's a vertical line. That's what I meant. The molecular gas. So technically speaking, going back to your own papers, the real linear relation is between the mass in stars and the mass in dense gas. Okay, but then you can increase the density, and in the end you correlate stars versus stars. Because if you increase the density enough, it's going to be pointing at the stars. So you actually have a problem that even the H2 in itself is not a star formation rate tracer. You, by eye, see globally that it follows the spiral arms, but then if you look in detail, you actually are going to a much more fractal situation in which your stars are actually only tracing the peaks of the H2, not the entire H2.
Right, but I think there's a false argument there. When you say you go to higher densities, what we find is that you get to a certain density and there's a linear correlation. It doesn't mean that if you only looked at gas that was at, instead of 10 to the 4, 10 to the 5, it was 10 to the 12, that you get the same things. Obviously, when you get to stars, it breaks down. But on averages of parsecs, you have typical density of 10 to 4, 10 to 5. That correlates very well with the star formation rate.
Yes, and if you...
But also the low density, the gas that traced by CO also correlates with the star formation rate in a linear way, but it just has a much larger scatter, because what really counts is the fraction of that gas that's in dense form, and some clouds have lots
Right.
of dense gas, some clouds don't.
Exactly.
There's a general trend, if you take, calculate the total mass, you'll still see a linear trend.
But
You
you
don't see that in H1, it just isn't there. H1 is inert, and it doesn't add anything, you don't learn anything from H1.
well, you learn that without H1 you don't have H2.
Well, yeah,
So, I mean, you,
start with H1, but I'm
but-
saying in terms of the actual, and I also should say that one has to be very careful here, because how you interpret these diagrams depends on the questions you're asking. So
Right.
if I want to just know what the star formation rate surface density would be in a galaxy, if I plot it against H1 and H2, I can get a good answer. If I want to understand the physical mechanism of star formation, I have to go deeper than that. And that's where you have to really worry about whether H1 is inert to star formation and are you forming stars in molecular clouds. So from a point of view of star formation person, I'm trying to understand the physics of star formation. The Kaneka-Schmidt law is not very useful, actually.
but if you are trying to understand the star formation on a global scale, then it's extremely useful. In that case, you cannot neglect the H1 because you are missing a very important component.
You want to get in there?
So I have actually a question on the global picture. I usually deal with red and dead galaxies, but in those rare occasions when I get to start forming galaxies, I'm always struggling. Why are you guys working in terms of surface density while the galaxy is 3D? There is 3D Schmidt-Kennecat relation, but it's much less used. And what I can tell from my perspective, because I've been dealing with dwarfs, if you look in this plot from Kennecat 98, it's based on old data, which is mostly for giant spirals, and we know that from the time of Ken Freeman that all disks have the same surface density. However, when you go down the line in luminosity, you go to dwarf galaxies, this constant is not constant anymore. They become less dense, and so isn't it the easiest explanation why there's a break in the low density in this Schmidt-Kennecat relation, just because you have to operate in 3D when the geometry is not the same, and so the star formation is not initiated in the same way.
So the break is actually also seen in the disky galaxies, in the discless galaxies, when you look at...
It's disky, but if you go to low mass disks,
Yes.
disks with lower density, they're
Okay.
not constant anymore.
Right. So if I'm interpreting correctly, you're looking at the break in the molecular, so in the total gas, if you look at region by region, you have a linear relation and then a sort of a sharper break. So that is,
In the global,
yes.
there is in the
Yes.
lower end, on your plots, and on plots from both of your talks, there was in the global Schmidt-Kennecat relation, there is a break in the bottom of the relation. It's much more pronounced if you look at individual regions.
Yes.
And it's much less pronounced when you look global
Right.
at galaxy as a whole.
But the individual regions are not suffering from the flaring of the disk, so it's not the same explanation.
Yeah.
So actually, talking about the Schmidt-Kennecat law in global galaxies, how many of you are familiar with the dual relation, the dual tracks, the quiescent star-forming galaxies versus the starburst track?
I was going to ask you about that.
Right.
Is that
So-
dead now? Or
Huh?
is that dead yet?
No, it's not dead. So in Kingston in July, Rob gave a talk in which he went back and talking about all data. He actually revamped all his analysis with the most recent CO data and H1 data available. He's still looking at all galaxies, right? Because the idea is, can I explain what is happening at the global galactic scale? Then you can go to the cloud scale and try to understand the physics of the star formation.
I
But
interrupted her originally. Just to make sure everyone is on the same page, there's
Do we
some
have a-
people have claimed there's two different relations between gas density and star formation rate. A starburst track, which is more efficient, and a quiescent galaxy, or a star forming galaxy,
Yes, yes, yes.
forming galaxy that's like has a lower
Right.
efficiency, and there's an offset, and there's bimodal. That's what,
yes, so that's exactly the summary. So Rob showed this very interesting two plots, side by side. One showing the sigma star formation rate as a function of the total gas surface density, and that's the usual Schmidt-Kennecat total gas. And actually, this time the slope is no longer 1.4; it's 1.5 with modern data. Okay, local galaxies. Then he said, okay, then because I have the data, I separated the CO component. So the gas traced by CO, the molecular gas traced by CO, and there are debates on whether this is the full molecular gas component or not, but let's gloss over that. CO and star formation rate. And even in the local galaxy, you see two tracks. Quiescently star forming and starburst. So it's only in the same. Yes, Milky Way would be in the lower track.
And SMC is,
The SMC, no, wouldn't be. The SMC is not a starburst.
yes, okay, so it's still a little.
It's still low.
But by the way, that's also what contributes to the steep nonlinear slope of the Koenig-Schmidt law, because when you mix galaxies on one track with galaxies on another, you fit it with one.
Right. So what determines the two tracks? What?
Gas, dense gas. So what
But why do you have a jump? You shouldn't have a jump, right? If it's a question of a dense gas, you should.
jump because starburst galaxies, all the star formation takes place within an inner kiloparsec or 500 parsecs, and you're comparing that to something average over a whole disk. So the jump is because you're going from a completely physically different situation. You have a disk galaxies, which gives you the
But then
lower
why
track.
wouldn't it
So why don't you have galaxies in between? You have to have galaxies in between, because nature doesn't jump in that way unless it's quantum mechanics.
But there are points that go in between as well. I mean,
He didn't see any. He found two tracks.
But if you look at the old data, you see one track, and then you go up to another one, and then it's parallel. There's an area where they.
Not in the plot that he showed.
I didn't see that.
Yeah.
I think let's continue discussion over coffee. Can we thank the speakers here, or did you? Okay, great.